then I can do that. So,
Let me pull out the packet.
okay, so I think he taught you. Do you know what the names are of the methods he taught you? I think there's uh
Trig Sub, uh, parts, and I don't know what the other one is.
okay. Those are the only two I remember as well. I'm trying to figure out. Uh, all right, let's just go over Trig Sub and parts first, and then we'll see from there. Okay.
Do you have the packet on you?
No, I don't. I am taking BC, so I don't have the packet, but I
Yeah, I
can.
don't know where my packet went. Shoot.
All right. While you find that, I will go. I will explain. Let's do let's do
All right.
parts first. Okay. Let's say we have two functions. Uh, of x. Right. So u of x. Let me do a and b. Actually, that's probably better. A of x and b of x. Right. And let's say our function is equal to a of x times b of x. Right.
So you're saying y equals a times b?
Yes, and these are two functions of x, right? So this could be x, this could be x squared, this could be sine x, as long as they're functions of the same variable. So, taking the derivative of this with respect to x, we get dy dx is equal to the derivative of a of x times b of x, right? Let's do d over dx. And that's equal to, what is that equal to? Product rule. So, uh, let's just do this in prime notation. A prime of x, uh, b of x plus b prime of x, a of x, right? And so, uh, and so, just forget about this because I was just using y to define the function, but we don't really need that. So now let's just subtract one of these. Let's subtract this one onto the other side. We get d over dx of a of x times b of x minus b prime of x, a of x is equal to a prime of x, b of x, right?
Yeah.
And then if we integrate both sides with respect to x, right? So with respect to x, both sides, we get a of x times b of x minus the integral of b prime of x, a of x dx is equal to the integral of a prime of x, b of x dx. And that at first this doesn't seem that useful, right? It's just an expression that's kind of obvious, but it helps us when we have a function when we're trying to integrate a function. How do I say this? When we're trying to integrate a function that we can split up like this, and we can integrate each of the functions separately, but it's hard to integrate them together. So we can keep splitting them apart into two functions. And you know how usually when you take the derivative of a function, most of the time it goes down to zero, right? So like x squared, take the derivative x, 1,
Yeah.
0. It goes down to 0, right? So we can keep doing this process over and over again where we're splitting a function apart. We can keep doing that, right? Then we can split this function apart. Then we just keep doing that over and over again, and eventually we'll get something most of the time. Again, these are integration techniques, so obviously they don't always work, right? But this is one way. This is one thing you can do when you're to try when you're integrating.
Okay.
Okay. I think if you have a specific question,
I'll just send you the page itself, and you can just go through
yeah,
all
yeah,
of it.
that would be good.
It's only parts and trig sub, right?
I think so. I don't think you guys learn. Yeah, that should be all of it.
We didn't learn partial. I don't know about partial fractions. I don't know.
Oh, okay. Yeah, well, partial fractions. Did you guys learn it in class? Is that what you're saying? Because I
I
can
don't
go
know
over
if we
that.
did. Yeah, I don't know if we did or not.
Okay. Well, I can look at the questions and see if any of them need partial fractions, and if so, I can go over that. It's also pretty easy. So.
Okay. 1 second. I'm trying to send it. Okay, where should I put it? Homework. I'll put it in homework help. This is the first page.
Okay. Let's do. Let's do.
So start with number 1.
Yeah, let's just. Yeah, okay. That's good for parts. Let's do number 1. Can I erase this? Do you need it? So.
Yeah, go for it. You can erase it.
Okay. I'm going to erase this, and I'm just gonna put that expression we found. I'm gonna put it in terms of u and v because that's how I like to do it.
Integral of sine 7x cosine x. Yeah. Okay.
Sorry, I have to. Okay, there we go. So I'm just putting that in the corner. Okay, let's do number 1. Is that fine, or do you want to do a different one?
No, yeah. One's fine. We can just do most of them after.
Yeah, number 1 is good for parts, so I can show what I'm talking about. So let's just call this. Let's call this.
Oh, I thought I was talking about the first review by and integration by part, like number 1.
Oh,
Sine 7x.
okay. Yeah, we can do that. We can do that too as well. Yeah, let's just do that one. That's fine.
Okay.
So we want to integrate sine 7th of x cosine x dx. And okay, so I think let's for now I'm just gonna show you the process and then I'll explain you my reasoning for it. So let's call this dv, right? Or actually, since I called it that.
And he was doing some random stuff like UV, DV, DV.
Yeah, and basically what he's saying is he instead of using prime notation like this, he says u prime of v, right, is equal to uv. Sorry, my u's and b's look similar. Uv minus b du, and that's the same thing as this, right? This is du. There's v. This is u and v, and this is u prime of v, right?
So they're just two functions. Is that what you're saying?
Yes, yeah. He just likes to. This is just like the way people memorize it, obviously, because it's just letters and it's easy to understand. But yeah, these are two functions of x, and we found this relationship that we can use, right? Let's call this dv, right? Or actually, sorry. Let's do.
Should we call that du?
Yeah, sorry. That's what I was about to say. So that's.
Because that's the derivative of sine, right?
Yeah. So then if we call that du and we call this v, right? When we integrate that, that becomes sine, right? And so a lot of things. So now we have a lot of signs, and that's my logic for choosing this as du, right? We could potentially try calling sine 7th x dx du, but that probably won't lead us anywhere useful. So, okay. So u prime of v, right, which is also the same as v du, right? So that's why we're splitting this up into v du. So v du, let's, on the side I like to say du is equal to cosine x dx. So then u is equal to sine x. And then v is equal to sine to the 7th x dx. So dv is equal to 7 sine x cosine x.
No, isn't it 7 derivative of v is sine to 7? I mean, 7 sine to x.
Oh, 7 sine to the 6x cosine. Yeah, also, I just realized this isn't a parts question because if you look at it, right, we're still going to get cosine, and that's not really going to be that helpful, right?
Yeah.
So this is actually just a u to the 7th du. Right? Yeah, because not everything can be done by parts. It's usually done by parts if once we convert it to this, right? Once we convert our integral to this, if it somehow simplifies in some way. But here, it's just going to get us back to a cosine x, so we don't want to do that.
Okay, then you can do the number 1 where it says integration by parts, like the integral of x.
Yeah, okay. Yeah. Let me do that. So
all the methods easy to understand.
Yeah, all the methods are pretty easy, especially compared to what other people learn for integration. They learn a bunch of they learn parts, but for Trig Sub, instead of learning Trig Sub, they learn a bunch of other stuff, and it's very complicated, but it's pretty easy the way he teaches us. So anyways, this is dv and this is u, right? And the reason I do that is because when we create this relationship, u is the one we're going to take the derivative of, right?
Yeah.
And this is the function that boils down, right? X 1 0. It's the one that it converges. It doesn't actually.
Why did you pick e to the x to dv?
Because now, right, dv. The reason I chose this as dv is it's because it's kind of hard to explain. Can I do it and then I'll show you my reasoning? Yeah. Sorry, it's a little. So du is equal to dx, dv is equal to e to the x dx, b is equal to e to the x, right? So then that's uv. So x e to the x minus b du, which is e to the x, du is dx. And so the reason I chose x for my u is because now it boils down, right? So we get a simpler integral when we convert it. The reason I chose this for dv, there's not really a good explanation other than because we chose this for u, the rest is dv. I guess another thing is you can think about it like I can integrate this on its own, right? So that's a good dv because that's going to probably, it's also a non-terminating, like it's a non-terminating function because every time you take the derivative you get itself. So
is the logic for parts if you have two functions multiplied, is that when you use parts?
Yeah, when you have two functions multiplied and you can't just integrate it with any of the other methods you've learned, and you know that one of them boils down in some way, it's good to use parts there.
So x e to the x minus the integral of e to the x is just e to the x.
Yeah, so then this is your final answer for that. Oh, plus c as well.
Plus c.
Yeah, and let's do number. Yeah, and you can see number. I'll show you. Since it's pretty simple, I probably won't do a lot of these out. I'll just show you what I picked for u and b, and if you see how it terminates, we can move on. If you don't, then we can do the problem. So like for number 3.
Number 3, okay,
so that's 2x plus 1, and I'm going to say e to the negative x.
Yeah.
And yeah, and then now you can see this one terminates, right? This function terminates when you take the derivative.
E to the negative x. Okay, continue, you're saying?
Yeah, so this function, we can do this in one of two ways. One, we can distribute and then do parts, or we can just do parts straight, right? Because if we distribute and then split the integrals, then it'll just be a simpler parts problem. But I won't just because I'm trying to teach parts right now, I won't split it. So this function 2x plus 1, when you take the derivative, becomes a constant, then it terminates, right?
Yeah.
So we know that when we use this relationship, the function, our problem's going to get simpler somehow, right? So let's call this u, and then let's call this dv. Again, a pattern you'll notice is that our dv, when we take the integral, it doesn't simplify, or it doesn't get simpler. That doesn't always have to be the case. I don't want to say that's always going to be the case, because there might be some cases where that's not true, but generally that's what happens. So then u is equal to 2x plus 1, du is equal to 2 dx. Dv is equal to e to the negative x dx. V is equal to negative e to the negative x, right? So
v, so you took the integral, right?
Yeah. Right, I took the integral of both sides, so this becomes v, and then that becomes. And also another thing that, yeah, and then the reason we don't have plus c here is because this is, I remember I had an explanation for this. It was because if we did have a plus c here, the reason, wait, let's pretend there's a plus c here. Let's see what happens, right? We get uv 2x plus 1 times e to the negative x plus c minus e to the negative x plus c, and then I'm going to put the 2 in front, dx, right? And, shoot, I don't want to do this out, but I will say that this, when you take the derivative again, you do not get this. And the reason for that is because if there's a plus c here, you get extra functions, right? And then this has a cx, and you get extra functions. And so all we're doing here, another way you could think about it is all we're doing here is we're finding a product of two functions that will get us, we're finding the product of two functions that will get us this, right? You see how those two are the same?
Yeah.
So it's kind of hard to explain, and it's also why Mr. Shao doesn't explain it. But the reason there's no plus c here is because we want to find a product of two functions, right? Because the way we derived this was a product of two functions, where we get, actually a better way to explain it is it comes from the product rule, right? Our derivation of this. And in product rule, constants go away, right?
Okay.
So because it comes from the that's probably
that makes sense.
Yeah, that's the easiest. Yeah.
Wait, so then the dv, can you explain like the logic behind parts again? Like
Yeah.
thing up top, like the right side, like can you explain that? Like what does that mean? Like all of that uv, like I know that's the function multiply times minus the integral of second function, but like
So
how do you just like automatically know which one's v, which one's u, which one's dv, which one's u? Like, you get what I'm trying to say? Like, I don't
yeah,
know.
I see what you get, what you're trying to say, and it basically the logic for picking. Do you understand where this comes from? The product rule, or do you want to see that again? Okay, so that's
I understand.
okay. So the reason I chose this for u and this for dv is the way I'm trying to the way I would explain it is u is your terminating function, right? Because in some problems you might have to do parts multiple times. The ones we've done so far, you only need to do it once, but sometimes you need to do it multiple times. And so if you choose the function that doesn't, that when you take the derivative you get the same thing, you're just going to keep doing parts endlessly, because you're going to get this same thing. You're going to get you're going to get this, or sorry, if we call this u, right, and then we call this dv, right, this function would get increasingly complex, right? And then this function stays the same. So that doesn't really help us, right? Because right, 2x plus 1, if we integrate that, we get x squared plus x, and then we integrate that again, right? Because we'll have to, right? Because none of the functions are going to terminate when we do parts, so we're going to have to try parts again. And when we do that, we get x cubed over 3 plus x squared over 2, and it just gets messier, and it never resolves. Versus if we pick our terminating function for u and our non-terminating function for dv, this function is going to get smaller, and at some point it's going to become 0, right?
Yeah.
So we know for a fact that if we kept doing parts, this expression is going to get simpler enough to where we can integrate it. We can actually integrate it.
Okay. So basically, non-terminating function is your dv, and your terminating function is your u.
Yeah, and just think about it like that for now, unless we come across, because there might be problems where the logic is a little bit different, but for now I think that's usually the logic you go with. In fact, it might be the logic you go with all the time. I just haven't done a lot of parts lately, so I don't remember. But
that should be number 4 now.
Yeah, I can do number 4.
That one is there's no second function, so I don't know how you do it.
Ln 2x dx from 1 to 4. And okay, so we can't integrate, we don't know what function the derivative is ln x, right? We don't know that. It's not something we can integrate simply. And so this, and when you take the derivative of this, does it get simpler? Okay, no.
Derivative.
Yeah, it doesn't, and then, right, and then, take the derivative again. So it doesn't get simpler, and so this is where the logic I was talking about kind of breaks down. But what I will say is it, once we take the derivative of this, can we integrate it? Like 1 over 2x, right? That's the derivative of ln 2x. We can integrate that, right? We know how to integrate that. Mm-hmm. And so if we choose this as our u, and you can actually just choose dx as your dv, right?
What's the logic behind it? Like, why do you just pick the whole function as u and the other one is?
Because when we're doing parts, you have to pick a u and you have to pick a dv, right?
Okay.
And so when that is a good question. I'm trying to figure out like the best explanation. But if I pick the whole thing as u, then my dv is going to be 1, right? And if I did that, when I take you can't. Oh, also another thing is, you can't take. You can't take the function. You can't take the derivative of x dx, right? You can't have a dx in your derivative. Or actually, you can. Sorry, that was a bad way to say it. But basically, it just gets. If we chose. It's a good question. Alright, give me 1 second. I'm gonna do something on the side. Okay. Alright, what was your question again? Why we picked that U and why we picked that V, right? Mm-hmm. Okay. So another way you can think about this, other than picking, instead of trying to follow and pick a U and V, instead of trying to follow this expression he gave you, you can also think of it as, if we go back to the roots of this derivation, right? It's a product rule, right? So all we're trying to figure out is, what two products can I have so that I end up with this somewhere, right? When I take the derivative of those two products. In this case, we could try ln 2x. Let's just try that, right?
Derivative of x ln 2x?
Yeah. So that's f prime of g plus, plus g prime of x. Is that about right? Yeah, that's right. 1/2. Wait, is the derivative of ln 2x? The derivative of ln 2x is 1 over x, right?
Or 2x times 2, yeah, 1 over x.
Yeah, okay, so then that becomes 1. So that's ln 2x plus 1 is equal to d over dx x ln 2x. Right? And then if I multiply dx on both sides, right? And then I can integrate both sides, and I get.
You said that. Oh yeah, okay.
And so you see how, so that's just, these two are the same, right? and so plus and then 1, right?
Yeah.
And that's equal to, and then this is, you can think of this of two ways. You take the derivative and then integrate it. You can also, something that people don't realize is, you know how we do dx, right? And this is just x, right? Just something that people it doesn't click in their head. This is basically the same thing, right? We're just substituting that for that, and so that's just equal to whatever is on the inside as well.
Okay.
So anyways, so this would be um so this would be x ln 2x is equal to ln 2x dx plus 1, and then we can subtract that onto that side, and we get ln 2x dx is equal to x ln 2x minus 1. And you see how we didn't even think about, I wasn't even thinking about which one do I pick for u and which one do I pick for v, right? I was just thinking about what two products can I get so that I have an ln 2x on this side, right?
Okay, that makes sense.
And so I'm trying to figure out, because that isn't that great of an explanation. I'm just trying to figure
It's
out.
good. I mean, like those type of questions, like I try and get like the basics down for like I'll ask them in class tomorrow. But like if you can do more problems that are like get a clear pattern, like I get the hang of it. Then like tougher problems, like ask people around. I can ask Shayo. Like it's good. Like you did your best. I appreciate it.
Yeah, it's yeah. I don't want to say that it's just practice, but for parts specifically, there are like a lot of patterns that you like. Once you do the problems, you'll realize. It's kind of just a bad way of explaining it, but like that's right now that's the best I can give. I can think
That's
about it
fine.
and I'll come back to you, but for now, yeah. So
Okay,
let's,
number 9.
yeah, and so this one you know how to pick. That one's U and that one's TV, right?
Yeah.
Because then this one terminates easily, and this one is just, it's the rest, and it doesn't bother us. So that's why. That's okay. And so number 9 would be 8x plus 7 ln 5x dx, right? And
Will the first step be the functions multiplied, right?
yeah, so
And then minus the integral of ln 5x dx, and then that just becomes 8x plus 7 times ln of absolute value of 5x minus, what's the integral of ln 5x? What's that? That's 1 over 5x times 5, 1 over minus 1 over x.
so the thing is, this isn't a this isn't dx here, right? This is du. So the thing you're gonna have to remember is uh so the thing you're the main thing is, the problem with that is that when you take the derivative of this, you get 8 dx, right? So that's something you forgot when you told me that. It's u and v, yeah. 8x plus 7 times ln 5x minus u v du. This is du, right? V du. So
Minus
that's
v du, yeah. So v
times 8 dx.
huh?
Because it's v du and our u is this, and so our du is 8 dx. So you need to multiply v by du.
I'm confused.
Okay.
Minus integral of v d, is that v dv or v du?
Du. Yeah, that's probably du.
Okay. Yeah, okay, then that makes sense. But like, how did in the formula, how did you get u v minus integral of v du? I thought it was v dv.
I can let's go through it one more time. So I'm gonna just use the simplified. I'm not gonna go through defining functions and stuff. So uv, right? D over dx of uv, that's equal to
Okay.
u prime of v.
Yeah.
Plus v prime of u, right?
Yeah.
And so if we multiply both sides by dx and then take the integral, we get uv is equal to the u prime of v dx plus v prime of u. Actually, I'm going to remove the dx just to make this more general.
The derivative of uv is product rule. Okay, I understand what's going on from there.
Mm-hmm.
Then.
And so once we take the integral of both sides, right, we get uv is equal to
uv prime plus the integral of uv, but yeah, okay.
And then
I figure out the dx's.
You can also do this without dx's because I'm not using any notation. These are technically it's a notation thing because you actually, when you're using prime notation, you don't even need a dx. That's one of the reasons I don't really like prime notation, but this is valid because it's implied what you're taking the derivative with respect to. It's a weird notation thing. I can actually, let me just add the dx. I can also do that too. I can put the dx over here and then is equal to u prime of v minus or plus v prime of u, and then we multiply both sides by dx, so I'll put a dx here and then a dx here. I'll take the integral of both sides, and then this becomes uv is equal to u prime of v dx plus v prime of u dx.
Yeah, okay.
And then we can pick whichever one we want to subtract. But for the sake of matching it with whatever I just the expression I made, I'll subtract this one, right? So I'll put that onto that side, and that becomes u prime of v dx.
All right, I see it now. Yeah.
Okay. Yeah, and then u dx is du as well.
Yeah. Okay, that makes sense. So then for the problem that number 9, it'd be the two functions both. So 8x plus 7 ln 5x minus the integral of ln 5x 8 dx because it's du, v du, and du is 8, so 8 dx. Okay, yeah, that makes sense. And then you solve the so that you can pull out the 8, right?
Yeah, and then it's 8
minus 1 over x. It's just minus 8 over x.
You actually have to do parts another time because we don't know this. You're telling me that this is equal to this, which is not true. The derivative of this is equal to 1 over x. So this is one of those times where you have to do parts twice, actually. So let me zoom out. Can I move?
So then, just work out. Let me see what you do.
Yeah, so 8x plus 7 ln 5x minus this, right? And then I'm just going to put a line here. So let's do parts again. Let's call this dv, like we did with that other ln problem. Let's call that one u. And so u is equal to ln 5x. du is equal to 1 over x. dv is equal to dx. v is equal to x. So this becomes uv, so x ln 5x minus v du, which is, there should be a dx here. So 1 over x dx times x is equal to dx. And so that's dx, which is x. And so that's x ln 5x minus x. And then remember, yeah, there's a minus 8 out here, so we got to put that in. So the final answer is 8x plus 7 ln 5x minus 8x ln 5x plus 8x. Yeah, so that's our final answer.
Plus c.
Oh, yeah, plus c.
Okay. So, parts isn't that bad.
Yeah, the thing with parts is that, yeah, I guess you just have to do a lot of problems. Usually, there is logic to it, but it's kind of hard to explain. like here, I would tell you that the logic is this function terminates, this one doesn't, right?
Yeah.
And then once we do it again, okay, look, it's an ln dx. We know how to do that one, right? That's kind of the logic I would say there. And you kind of have to have you kind of have to think ahead a little bit as well. So yeah. Okay, so that's kind of parts. Is there any of them that you don't think you can do with parts?
For number 8, that looks like a problem that you would do U sub with, right?
Yeah, and actually, I think, yeah, let's just do that one. Actually, let's do that one.
But can you do number 11 first? I'm trying to do it on my own. Like I don't know if I'm doing steps right.
Oh, okay, yeah,
We can do 8 afterward. Yeah, no problem.
All right, number 11.
So my intuition is telling me that there's two functions, negative 6x and the cosine 5x.
Uh-huh.
My intuition is telling me that the negative 6x is the u, and then the cosine 5x dx is the dv.
And why is that?
Because negative 6x will terminate. Negative 6x will become negative 6, and then the derivative of any constant is 0.
Yeah, and then this one doesn't terminate. But that's fine because... Yeah. Okay, so...
Cool. So then it just be...
Do you need me to do it out? Because after that, yeah.
I'll do it, and I'll say my thought process out loud, and I'll just correct me if I do anything wrong.
Okay, yeah, I can do that.
Okay. So negative 6x times cosine of 5x. Negative 6x times cosine of 5x minus the integral of cosine.
Oh, watch out. So it's negative, it's u times v, right? Our v isn't cosine 5x, that's our dv. Cosine 5x dx. You need to take the integral and find v.
Right.
Yeah, that's why I still do this to this day, where I just write them out on the side. That way I know which one is which.
Okay. That's when you find the integral of cosine 5x. Missing a 5, so add a 5, pull out, and then 1/5, right? 1/5. Why am I struggling with this? Cosine of
5x.
It is 1/5 sine 5x, right?
Yeah, because you need to offset the 5 that's created with the 1/5.
Yeah. So that's right? So negative 6x times 1/5 sine of 5x.
Yeah.
Okay, and then just put that in brackets minus the integral of v du, right?
Yeah.
And v is 1/5 sine 5x.
And then du is
negative 6 dx.
Yeah, and then from there it's easy, right? This is doable.
I'm not gonna actually do. I'm just gonna so you pull out the negative 6.
You can pull out the 1/5 as well. So
yeah, both of them. So you can pull out a negative 6/5, and then you just have sine 5x dx, and you can just do the integral of that. Okay, and that's it, right? And
yep.
You just combine it all together.
Yeah, and then plus c. Yeah.
Huh. Okay. I need to be careful about that. So it's the formula, or not the formula, but it just u times v minus the integral of v du.
Yeah.
And the du. Okay. Yeah. Okay. I think I got it.
And I would highly recommend just writing them off to the side whenever you do that.
Yeah, for sure. All right. Go on to number 8. You said you.
Yeah. So number 8 is. So 8 is x cubed square root x squared plus 2 dx from 0 to 5. Okay. This isn't the parts section. This isn't something I would do with parts usually. But yeah, I would.
It's not. You do U sub, right?
Yeah, I would usually do U sub, but okay. You can do this with parts. And actually, no, I see what he's trying to do here. So basically, when you do it with parts, right? this function terminates. This one gets more complicated,
Oh,
but at
which
the
one
same
terminates? The x to the third.
yeah,
Second,
and
three
this
x squared.
one
Yeah.
and this one actually gets more complicated when you take the integral. But the thing is, it also gets more complicated when you take the derivative. So it's not something we would want to take the derivative of because it wouldn't really get us anywhere. Versus here, it might get us somewhere. And actually, if you have a little bit of foresight, you'll realize that like this will eventually become an x, right? And then we'll have an x square root of x squared plus 2. And then, that's just u du. So that's something, yeah. So
I
that's,
just work it out.
yeah. So du is equal to 3x squared dx. dv is equal to square root of x squared plus 2 dx. b is equal to whatever the integral is.
You take the integral of both sides, right? Like to get v, you take the integral of dv.
Oh yeah, and then you take the integral of both sides. And so actually the interesting thing here is that something we can take. This is actually a cool problem because it's both a triangle problem and a
Triangle.
yeah, it's a triangle and a parts problem at the same time. Unless is there some way I'm missing?
Triangle.
Is there some way I'm missing to take the derivative of this that you know?
X squared plus 2 to the 1/2. And then you can just, I don't know.
Yeah, because if you tried u to the 1/2, your du would be, what is it? 2x, and we don't have that. And so this is actually where you would need to use a triangle. And the way you do triangle,
Trig sub, right?
yeah, trig sub. And so the way you do that is, let's just make a triangle, right? With these terms, let's make a triangle so that one side of it is square root of x squared plus 2. A right triangle, right? So I can make this x, I can make this root 2, and then this one over here would be square root of x squared plus 2. And our angle theta over here, right?
Why is the other one root 2, other leg, and why is the other one x?
You can actually flip them around. It doesn't matter.
No, but why are those the legs? Where did you get x and root 2?
Because I needed to make a triangle where one side was this, and you need these to be the sides for that to be square root of x squared
So
plus
it's
2.
Pythagorean theorem, right?
Yeah. And you could also I don't know, you could probably put this over here and like 1. But then that just gets more complicated, right? Because now you have x squared plus 2 plus 1, and now you have x squared plus 3. And you'll see why that's more complicated, and you don't do that in a little bit. So that's theta. I called my angle over here theta. This is x, that's root 2. And so that makes this side and those match, right?
Yeah, okay.
And now I can create this in terms of our triangle. So square root of x squared plus 2. How do I get that out of this triangle? Well, I could say cosine theta is equal to root 2 over square root of x squared plus 2, right? And then I can use algebra to isolate that. And now I get root 2, let's just make that secant theta. Right? Yeah. So that's one piece of our puzzle. We also need a dx. And the easiest way to get a dx here is tangent theta, which is x over root 2. And then let's multiply root 2 onto the other side.
So root 2 tangent theta equals x.
And then if we take the derivative, absolute derivative, so that would be secant squared theta d theta is equal to dx. And now we have a dx. And now we can rewrite this in terms of theta.
Okay.
And now this becomes, I'm gonna, I'll see if I can fit it up here. So root 2 secant theta, right? That's x squared of x squared plus 2 times root 2 secant squared theta d theta.
D theta, okay.
And so that becomes 2 secant cubed theta d theta. And we know how to integrate this.
How'd you get 2? Oh, the root 2. Okay.
Yeah.
Yeah, okay.
So
secant cubed is, how would you do that?
It's another parts. So this one was a very interesting problem, right? Because now it's secant.
Yeah, everything.
Yeah, so this would be I could say this is dv, right? Because now that becomes tangent theta, and then this becomes secant theta tangent theta, right?
But how do you know? But none of them terminate. How would you know which one's dv, which one's u?
Well, I would argue that if we make this dv, it goes from a square to just tangent theta. So I would say that that does terminate. And so
Yeah,
actually,
exactly. So shouldn't that be u?
yeah, so that's what I was about to say. If we make it u, it doesn't uh it if we make this, there's two reasons why we don't want to make that u. One reason is if we make this u, then we get dv as secant theta d theta, which gives us an ln in our integral when we do it out. And do we want an ln in our integral? Not really, because that either requires more parts or it's just not possible, right?
Huh.
And
But then
another,
wouldn't secant would become secant theta? That would become more complicated. So how? Oh my god, this is okay.
yeah. So this is why he actually makes you like know this. He'll ask you how to do secant cube theta d theta, but um, the reason it doesn't get more complicated, actually, how about this? Instead of doing parts, you can do parts, but actually another way to do it, that's probably easier. Actually, is secant squared theta times secant theta, right? Instead of doing parts, we know that secant theta is sine squared plus cosine squared is equal to 1. So tangent squared plus 1 is equal to secant squared, right? We know that's tangent squared plus 1.
Yeah.
And that's secant theta d theta. And now we can, is there any way to, actually, yeah, never mind. It doesn't work. Because if we distribute it out, we get a tangent squared secant theta, and that's just even more. That's even more. So, yeah, the only way you can do this by parts. So let me zoom out. Actually, I'll just make that really tiny. And so let's just integrate 2 secant cube theta d theta, right? Well, yeah. So secant squared theta d theta times secant theta. And then let's just call this our dv, and let's call this our u. And it doesn't make much.
I'll just take your word for it. I don't know why.
Yeah, it'll you'll see why later, but there's not. Yeah, you'll see.
Okay.
Hopefully, secant theta, right? Du. And so actually another thing I want to say with parts and trig functions, it's a very different logic because trig functions are always cyclical, or they don't terminate, right?
Yeah.
Derivative sine theta, cosine theta, right? Cosine theta, or derivative sine theta, cosine theta, negative sine theta, secant theta, whole other thing, right? So they don't terminate, but what we can do is if we choose our right u and dv, hopefully we can use trig identities to simplify afterwards, right? And so you'll see why I'm talking about trig identities. So secant theta tangent theta d theta, right? And then dv is equal to secant squared theta d theta. V is equal to tangent theta, right? And so uv secant theta tangent theta minus v du, right? Actually, this one's very interesting. Let me write it on. Actually, I'll write it on this side. Uv secant theta tangent theta minus v du tangent squared theta secant theta d theta, right? Well, what's tangent theta? We just figured that one out. It was secant squared theta minus 1, right? And so I'm going to move over to this side. It'll be secant cube theta d theta is equal to secant squared theta minus 1. So that'll be secant theta tangent theta minus secant cube theta.
Oh, by the way, are you recording all this?
Oh yes, I am recording all of it. So, secant minus secant theta d theta, right? And so, if I split this integral apart,
Yeah. God, this is a huge problem.
yeah, it is. Wait, hold on. Everything.
You basically just taught Trig Sub right now, right? Like,
Yeah, that triangle that I made over there, that's trig sub.
oh, and there's also changing variables.
Oh, okay. So that's kind of like a variation of it's like an extension of trig sub, and I'll talk about that in a little bit. I just need to figure out. Oh, this does work. So at first you think like, okay, we just got back to where we started, right? But we know that these two are equal, right? These two are equal.
Yeah.
And so what we can do, this is now algebra actually. So then we just add it to the other side, and we get 2 secant cube theta d theta is equal to secant theta tangent theta minus the integral of this, which is ln secant theta plus tangent theta, right? And so we can just divide by 2, and we actually just get the integral of secant. We found it, right? Because now we found what it's equal to.
Yeah.
And but I'm not going to divide by 2 because we actually have it 2 in our problem, so I'll just keep it like that. So we know that that's equal to this, right? And
yeah.
so when we did our trig sub, so let me zoom back in. When we did our trig sub, this was that was our when we converted everything in terms of theta, that's what we had, right? And that's equal to, so now v is equal to what was it? Secant theta tangent theta, right? And what's secant theta in our triangle? We can convert it back to x, right? So secant theta in our triangle is 1 over cosine. So that's root x squared. Let me split it actually. Root x squared plus 2 over root 2. Tangent theta is x over root 2 minus ln. Secant theta is squared plus 2. And then I'm gonna simplify it prematurely, plus x over root 2, right?
Yeah.
So that's the whole thing in terms of x. And so now we have to do, yeah, wait, hold up. This might actually not be, I'm not sure how you would do this with parts actually. Because this is just, yeah, because then once you do that, it just gets more complicated. And if you chose the other way around for u and b, that doesn't help. Oh, you know why? Because that's not an x cube. That is not. I misread the problem actually. Whoops. Can I clear this? I'm just gonna make a new one actually. That was not x cubed. That was x cube root. That was a cube root. So I actually just misread the whole problem. That's why it didn't work.
Okay.
Yeah, because if it was x cubed, you could just do u sub, and that would be easier. But I mean, kind of a good thing, because then I just taught trig sub and all that. But anyways, so that's our actual problem, and that is still not. This is still not. Yeah, this is still not. This is still just u du. So I don't know why this is in the
Part section.
Yeah.
It's okay. I actually have to go now.
Okay.
Like, if I don't know if you can
I can do.
I can send you the page and you can like just like you're recording the video anyway, right?
Yeah.
Just go over a couple of the questions, like the basics and like the methods, and like I can just watch the video later on.
Uh.
And then like see what you can try to say. If it's
Yeah.
okay with you.
Is it okay? Cause I would rather have people here when I do it, so I can do one next week and we can go over more of the problems and stuff. Just
Okay.
one last thing with the U sub or whatever it was called, the last thing you were talking about. It's
Yeah.
essentially instead of converting it back to x once we do trig sub, we can
Yeah.
plug in the lower bounds and the upper bounds. So let's say it's like x from 0 to 1, right?
Yeah.
These are in terms of x, right? Well, instead of converting it like, let's say that was, this is obviously not true, but let's say it was sine theta, right? We can
Yeah.
instead of converting it back to x, we could plug these in terms of theta. So x is equal to 0. We know what this is in terms of x. Let's say that's square root of x cubed or something, right?
Yeah.
That would be theta equals 0, right? Because we know what that is in x. And then x is equal to 1, that's square root of 1 cubed, which is 1. They're the same bounds in this problem. Does that make sense? I was just trying to, yeah. You would just, instead of converting it back to x, you would actually just convert the bounds and do it that way.
Okay. Oh yeah, I'll just like master parts, I guess, and then are there any good YouTube videos I can watch for Trig Sub?
For trig sub, they don't teach trig sub usually. I'm not 100% sure about trig sub. For parts, you can always people always do parts, so you can look at that online. But trig sub, just search up trig substitution and see what you get. You might not get anything.
Okay, let me set
So
just I'll send you one problem. Just like tell me how to set it up.
yeah, okay, I can do that. I can do that. Yeah.
Yeah, I'll send you the picture. Uh, is that also easy? It's in homework call.
Oh, it's the same image.
It is.
Yeah.
Okay, let me resend it then. You're a sophomore, aren't you?
Yeah.
In BC, yeah. I remember you were in my IM1 class and think when we were
Oh,
in
oh
sixth
wait.
grade.
Okay, I think I know who you are then.
I sat next to you.
Yeah, yeah.
I sent the picture.
Okay.
Did you challenge again?
I did. I skipped IM3 and then I took pre-calc in 8th grade.
Yeah, we're crazy.
Okay, which one do you want me to do?
Anyone.
Okay, I'll do number 1. If you need to leave, that's fine. I can just talk about number 1 and then I'll upload it.
I can say for number 1.
Okay. Square root x squared plus 36 dx. Well, we can create a triangle. We want an x squared plus 36, right? So we can make this 6, we can make this x, and then now that leaves us with x squared plus 36 on our hypotenuse. Sometimes you'll have a minus, right? And then if it's a minus, instead you want to put, you want to put 6 over here, x over here, and then you'll get x squared minus 36 or something like that. You can always just mess around and see what it is. But anyway, so that's x squared plus 36. So x 6 square root of x squared plus 36. We want this. So the easiest way to get that is cosine theta. And so that's 6 secant theta. Okay, so that's 1. And we want, we need a dx too. So dx would be tangent theta is equal to x over 6. So 6 secant squared theta d theta is equal to dx.
Okay.
So now we have and actually we need a 1 over. This is a 1 over square root x squared plus 36. So this is not right. I just need to divide by 6 here. So 1, so cosine.
You can just pull up the 4, right?
Yeah, I can always just pull out the 4 and add it in back later, so I'll do that.
Yeah, okay, that makes sense then, yeah.
Yeah, and then that's equal to, yeah, and then once you do that, right, once you do that, you can multiply these together, and you get 6, because there's a 6 here, right, so you need to remember that part, and then 6 over 6, actually, so they cancel out, so never mind. So 6 over 6 So cosine theta d theta. And then you know how to integrate that and then turn it back into terms of x.
Yeah.
So then your final answer would be, wait. That is not what the answer got. Hold on. 6 over. Oh no, it is what they got. Never mind. Wait, it isn't what they got.
They got 4 ln of whatever the hell that is.
Yeah.
I have to go, but once you figure it out.
Yeah, I'll figure it out. Yeah, that's fine. Yeah, I can do that.
Appreciate it, man. Take
Yeah,
care.
thank you. All right. So, square root. Trying to figure out. Oh, actually, we were on the right track. It's just secant theta d theta, not cosine theta. So then it becomes ln secant theta square root x squared. Once we turn that back, right, this is secant theta tangent theta, right? And once we turn that back into terms of x, it's square root of x squared plus 36 over 6 plus x over 6 plus c, which is what he got. So yeah, that's trig sub.